Today we'll be discussing something known as a rational function. More specifically, rational functions that contain oblique asymptotes. Now there are many different types of oblique asymptotes, and the type of asymptote is dependent on the difference between the degree of the numerator and the degree of the denominator. For example, a linear oblique asymptote could have an equation such as this, in which the degree of the numerator is 1 more than the degree of the denominator. The graph of this equation would look as such. Now there's another type of asymptote that we will be discussing today, and we'll be focusing more on this one than the linear, and that is a quadratic oblique asymptote. Now the formula for a quadratic oblique asymptote could look like such, in which the degree of the numerator is actually 2 more than that of the denominator. So in this case it's 2x to the power of 3 over 2x to the power of 1. The graph of this will look like that. Now, the equation that we will be studying today also has a quadratic asymptote, and it is such: 2x to the power of 3 minus x squared minus 4x plus 3 all over 2x. From this, we will be determining things such as the family, the intercepts as well as what the graph of this would look like, the domain and range of this graph, any asymptotes or holes, intervals of increase or decrease, as well as the instantaneous rate of change at 3 different points. All rational functions can be defined by the equation seen on your screen. F of x is equal to ax plus b over cx plus d. However, as the functions become more specific, so do their families. The family of our specific function would be considered thus: f of x is equal to ax cubed plus bx squared plus cx plus d all over ex plus x. The second equation would be the general family of our specific equation. Before anything else can be done, we must graph the equation. To start off with this, we will attempt to find the x-intercepts. We will start this process by trying to find a value of x that will make the numerator equal to 0. We will start with 1, as it is an easy number, and as you can see, after the math is performed, it is actually possible to say that x minus 1 is a 0 of our graph. Once a 0 is determined, line division can be used to simplify the equation down into quadratic, so that quadratic formula can be used to calculate the other 0, as seen on this slide. From the found zeros, a final equation can be found as such: g of x is equal to x plus 1.5 squared times x minus 1. Please note that all these calculations were performed on the numerator position of the equation. In the case of all rational functions, there is both a horizontal and vertical asymptote, as well as sometimes whole. However, in the case of a vertical asymptote, it is simply determined by what number would make the denominator equal to 0. In the case of our function, it would simply be 0, since 2 times 0 is still equal to 0. So therefore, the vertical asymptote of this graph would be at x is equal to 0. The process for determining the oblique asymptote of a rational function is quite simple, while still tedious, as you only need to divide the numerator by the denominator. The math for such calculations would look like such. This means that h of x is equal to x squared minus 0.5x minus 2 would be the equation of the oblique asymptote of our function. Any remainders are simply disregarded. A hole in a rational function occurs when a factor can be cancelled from both the numerator and denominator positions of the equation. As this is not the case with our function, there are no holes. Now that we know the asymptotes of the function, it is possible to determine both the domain and range of the equation. The domain is simply x is equal to all real numbers such that x cannot equal 0, and the range is y is equal to all real numbers such that y does not equal x squared minus 0.5x minus 2. These would be written as this. Now that we have all the asymptotes and the holes and all needed information, it would be possible to draw out the graph. However, since I unfortunately do not have a camera to record me drawing out the graph by hand, I have done it in Desmos instead. Here you can see what it would look like, in which the blue is the graph itself, and the green would be the asymptote. The vertical asymptote is not shown, as it is simply on the axis along x equals 0. So what is being asked when it says the intervals of increase or decrease is where on the graph is the line going downward, or where is it negative, and where on the graph is the line positive, or where is it going upwards. For example, on this graph, if we look at the blue line, it is positive, so x is increasing between 1 and infinity. So at this point right here, that's when the graph starts to increase. But before then, in this area right here, the graph is still decreasing, thus giving us these two equations. X approaches infinity between 1 and infinity, and x approaches negative infinity between negative infinity and 1. Although not mentioned before, we will also be determining the end behaviors of our graph. The end behaviors of a graph are simply, what is the graph doing at the very extremes? So, as x approaches either infinity or negative infinity, what is happening to y? However, a graph also has a vertical asymptote, so that will also be taken into account, giving us these three formulas. As x is approaching infinity, y is also approaching infinity, as you can see in this graph here. However, as x approaches negative infinity, y also approaches infinity again, as you can see right here. However, as x approaches 0, which is our vertical asymptote, x either approaches negative infinity, which you can see down here, or it approaches infinity right here. So, in conclusion, we have determined from this equation the general family, the x-intercepts, any asymptotes or oblique asymptote, the lack of hole, what the graph would look like, the domain and range of said graph, any intervals of increase or decrease, the end behaviors, and the symmetry. That is all for this presentation. Thank you very much for watching, and I will see you guys maybe in the next video.